But you got the important stuff. So I'm going to probably stay over here a bit towards the microphone just in case my voice does give out. But if it was at all like yesterday, my voice actually gets better. So we'll see. Now, there are a couple things that some years I have changed on this page. This page over here, the intro to the fundamental theorem. This is, remember, I was saying the why. Why fundamental theorem of calculus is true. This is not the forever card. This does not need to be memorized. But here's what we need to figure out as to the problem that's being tackled, the problem that's being solved. We have seen that the definite integral from a to b of the function f of x dx, which you guys worked a lot in section 4.3 on. Like, what's the idea? It's area. It's area from a function to the horizontal axis between an a to b. That can be approximated with rectangles or with trapezoids, but it can be found exactly if we take the limit as n goes to infinity. So an infinite addition or an infinite addition of infinitesimally thin rectangles will get us if it converges, will get us the definite integral. So how on earth can an infinite addition of infinitesimally thin rectangles equal one single subtraction? That's the question. How can an infinite addition equal one subtraction? Now, an infinite addition of bases times heights under a function f equals a single subtraction of, wait, capital F, who was that guy? The antiderivative. Well, we did antiderivatives at the beginning of chapter 4, at the beginning of the semester. We were taking a function and going backwards. But what does that have to do with anything? And it all comes back to this little MBT. So we're going to zoom in on MBT. We're going to zoom in on this page because, as you guys can tell, I think there's going to be a lot going on. We're going to zoom in on him. Let's go to 100%. Let's see if that's better. We're going to remind ourselves of MBT and what MBT guarantees us. And then we're going to say, remember when we do rectangles, we split up a section from A to B. We split up a section from A to B into n subintervals. So we have all these different, like on the number line, we have all these different x's. And in each of these subintervals, what can we say by MBT? So a quick reminder, if it helps, you might want to put this down with a number line. This is what we would do with Riemann sums. Remember, we would go ahead and split this up to be, okay, we have x1, we have x2, we have x3. It only goes up to x of n minus 1, because then the nth subinterval gets us to the b and we're done. But that could be 10, that could be 100, that could be 1,000, that could be 1,000,000. But as we section this up into more and more and more subintervals, each of them gets smaller, thinner. Basically that partition that we saw yesterday, the double lines of the delta is going to 0 as n goes to infinity. So all of that leads us up to, well, leads us up to this right here, but let's talk about MBT. MBT, a function is continuous and differentiable on, or continuous on a closed interval, differentiable on an open interval. Then there exists, okay, here we go, ready? There exists an x equals to c. Now, I'm going to actually, just in context of what's written, I've gone back and made these all c's before. I'm not going to do that today. So we're going to call c x star. Where's my little x star? Yeah, my little x stars. Okay. So there exists an x equals c equals, we're just going to call it an x star. There are different ways of doing it. Some people call them c's, some people call them x stars. It doesn't really matter. Special x, that's all you got to know. There's some sort of c, aka x star, within each subinterval. Now hold on. If this is true within each subinterval, then technically there's going to be lots of different c's and there's going to be lots of different x of i's. So because for each subinterval, this holds true, this holds fast, then we're able to go ahead and say, okay, well, what's going to happen in each one? So the first one, first subinterval, there's going to be this statement that's true. The second subinterval, this is going to be true. The third and the fourth and the sixth, 6th, 10th, 100th, 1000th, whatever. So we have to open up the possibility for there being lots of different ones, and that's, you can see what I'm doing here as far as opening up lots of different subintervals, so lots of different special guaranteed x values. Hold on, but what does MBT say? There is a special x within each subinterval such that, what's the conclusion of MBT? average equals the instantaneous. So give that to me in equation form, so such that, yeah, f of b, but I'm going to do capital F of b because we're going back. We're not using little f who's inside the integral. We're going back and saying average wouldn't be using the derivative. Average would be using the original. So average would be using capital F of, now hold on, b. You could say that, but the problem is for each subinterval, well, we could say each subinterval a to b, but we're going to have to broaden that now that we have all these other ones. So we're going to do each subinterval f of b minus f of a all over b minus a is equal to some sort of special f prime of x star. So we can move this little f prime of x star times b minus a is equal to f of b minus f of a. And then we could change this little b minus a to be a delta x of I. Now, I know that my pen got really thick for that little tiny space I was trying to fit it in, so let me show you what that means in context of any function inside an integral between an a to b sectioned up into n subintervals. And n can be going to infinity. I could say, for the first subinterval, there is an f prime of x sub, wait a minute, hold on, who is f prime? Isn't that just little f? So f prime is little f. So technically, I don't even need to say capital F prime. I could just say little f. Little f of x sub 1 star. There's some sort of special x sub 1 that meets MVT. And that could be capital F of x sub 1 minus f of a. That would be the first subinterval. There's some sort of f prime of c multiplied by the b minus a, multiplied by the delta x of that first subinterval, where the instantaneous will equal the average, but I've moved that b minus a to the other side. Now hold on, wait a minute. Doesn't this look a little bit familiar? Look at your definition of an integral. Isn't this really just a base times a height according to our Riemann sum approximation? So it's saying that, oh, hey, the base times the height of a special, at a special x value. It's not necessarily the left, not necessarily the right, not necessarily the midpoint, not necessarily the random weird one that AP gives you in a table that you have to use. But a base times the height, an area of a rectangle, is going to equal the change in antiderivatives of each of those little baby pieces on that first subinterval. Okay, so that's a rectangle equals a subtraction. Whoa. But we could go ahead and we could go to the second subinterval and say, hey, there's another rectangle at some special x. It's called like a perfect rectangle. That's going to equal f of x of 2 minus f of x of 1. We could go to the next subinterval. We could say, hey, by MVT, there's another guaranteed little baby rectangle underneath f. That's going to equal, oops, sorry, now we're at x of 2, x of 3. How long can I do this for? Forever. So let's not go forever. Instead, let's just go to n. Because n can be whatever we want it to be. Now I'm going to go ahead and go to n minus 1. The n minus 1 subinterval. And the n minus 1 subinterval, remember, according to our number line, if we were to grab that back up, the n minus 1 is the one that comes up and lands on B. Remember, each of these can have rectangles. And the heights are going to just be at that special x where MVT says, hey, this has to be true for a continuous and differentiable function. So I'm going to end at f of b minus f of x of n minus 1. You might not totally understand what I just did, but give me 1 second. And let me show you what technically was right before f of x sub n minus 1. It's kind of hard to see if I just land there. Now I know that some of you guys are doing, well, let's skip 4 line. Okay, you can squish this in, you can squish this in. If I had gone one subinterval before, x sub n minus 2. And I got f of x sub n minus 2 minus f of x sub n minus 1. Didn't we just say that a definite integral adds up all the different areas of the rectangles within the n subintervals? Right? The limit definition of an integral adds up all these different bases times heights of n intervals. So I can go ahead and say this side is sigma. This side is sigma from I equals 1 to n of f of x sub I star times delta x sub I equals. Question, could I keep expanding this to be farther and farther and farther and farther? Could I go to infinity? The answer is yes. We already said we could go forever. What would end up happening if I added all those subtractions on the other side? Do you see it? Infinite addition. I could keep on going and going and going and going. MBT says there's going to be a special place where this rectangle is equal to this difference. All I need is more and more and more rectangles. It can be left, it can be right, it can be midpoint, it can be the guaranteed MBT one, which is what we're doing. What happens over here when I add? Why? What happens to everybody else? I thought we were going to have an infinite addition.
I have a question. Doesn't the minus of x sub n minus 1 not cancel those? There's like two negatives.
Oh, did I do it the wrong way? Hold on. I put in there because it was ladder minus former. It was supposed to be ladder minus former. Thanks, Ed. But wait, what was he seeing? And then he was confused. What happens if you have a positive f of x sub 1 and a negative, and you're just adding them? It's this minus that plus this minus that plus this minus that plus this minus that plus this minus that. A positive and a negative, what's going to happen?
Cancel.
A positive and a negative, what's going to happen? What's he going to do with the next one? What's he going to do with the previous one? What's he going to do with the next one? What's not going to cancel? An infinite addition. An infinite addition and a single subtraction. Happy. An infinite addition and a single subtraction. The fundamental theorem of calculus says this whole idea of infinitesimals is possible by going to the antiderivative and doing a single subtraction. It all technically comes back to MBT. So the nice thing is, do you have to memorize this page?
Yeah.
No. It's really cool because you have an infinite addition that you keep on expanding, but what's always going to happen? You're going to be left with f of b minus f of a once you go to whatever n subintervals are. What you need to memorize is this guy, which shows, hey, oh, I didn't actually show it, but you guys should know it because this is the limit definition of the definite integral, right?
Yes.
Alright. So, one quick thing that you guys need to write down on this, just to show that you understand what's going on. First of all, I need the function to be continuous, because if the function, the integrand is continuous, that means the derivative of the antiderivative is continuous, which means the antiderivative is both continuous and differentiable, which means MBT applies. There was a lot in that statement. A long story short, if the integrand is continuous, then the antiderivative is both continuous and differentiable, MBT applies. But I do want you guys to go ahead and remind yourselves of who who capital F is. The definite integral is a change in the antiderivative from a to b. So it's a quick reminder that capital F, we don't even need to write that because you guys have a definition of the antiderivative. Let's just go ahead and put capital F as the antiderivative. Remind me what forever card we're in? 33. Thanks, guys. So what was Jared doing in his video at the beginning of this semester? What was I doing? That one random time I solved an antiderivative and got 24 without using my calculator. You guys remember that we did the left and right, the midpoint, and I solved it wrong. Not the problem, but the technical way of finding the exact area. Yes, we could draw this. Yes, we could make rectangles under this. Yes, we could fit in 10 or 100 or 1,000. Yes, we could use a sigma and try to figure out like stabilizing like a 0.0000 stabilizing a certain number. Or we could just say, hey, what if we were to look at this as just an indefinite integral? If we look at this as an indefinite integral, wouldn't we want to find the antiderivative? So we would think of this as being the negative, can you track with me? 3/2 power. Negative because it's in the denominator. 3/2 because it's 1 and 1/2. X to the 1 times x to the half. When we have like basis, x to the 1, x to the half, we add it. 1.5 is 3/2. How do we actually solve? Like we always solved antiderivatives. It's been a while. Do you guys remember? Negative 3/2 plus 1. Oh, yeah. All over. Where's my plus c? You guys watched me do it the other day? We're going to be doing a big old subtraction. If we do a big old subtraction, the c is going to be in both. It's going to be subtracted and cancel out. It's actually okay not to write it. That's not right. So negative 3/2 plus 2 over 2 is negative 1/2. Oh, we could just make it x to the negative 1/2 times the reciprocal. You guys remember how we could multiply by reciprocals instead of dividing by fractions? But how many of you want to plug in a 1 or a 4 right now to that, how that looks? No, we don't think, my brain doesn't think in a negative exponential power. Like, so what if we do negative 2 over the square root of, is that better? X to the negative 1/2 says throw me in the denominator. Okay, the 1/2 says throw me under square root. Okay. Now, here's where the f of b minus f of a comes in. Ready? It's the change in antiderivative from a to b, but the subtraction is antiderivative of the top minus antiderivative of the bottom. This is my antiderivative. This is him rewritten in a pretty form, but it's of the top. We plug in the 4 first, the b first, and then we plug in the a. We plug in the b first, and then we plug in the a. So we plug in the top, which is 4. We plug in the bottom, which is 1. Now, if it was switched, if it was 1 on top and 4 on bottom, which is backwards, the subtraction would be backwards, which means the sign would be opposite, which is where that property comes from. We're subtracting a negative. It's the same thing as adding. Square root of 1, any power, 1 to any power is always 1. That's just going to be 2 over 1. And then this one, square root of 4 is 2. Dun, 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 dun. The answer is what? Wait, no. Oh, that's true. We were so close to getting 0, but not quite. Because what's 2 over 2? Dun, 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 dun. If it's 0, that sometimes means that it was like an even function where you had area above and area below between like symmetric bounds, and so they cancel. What we haven't seen so far is that area above the axis is a positive displacement, because think like if velocity is positive, we're moving right, and area below is negative displacement, because think about it, you're moving left. And so if it's 0, that means that you moved right and you moved left the exact same amount. Maybe all in one, or maybe like a little bits and pieces. If we're thinking about the application of integrals being displacement. Okay, you saw your first definite integral solved out after learning the fundamental theorem of calculus. So what does this thing tell you? To solve a definite integral of a function, what do you have to find first? The antiderivative. Now I'm going to actually put in, because I think it might be helpful. Maybe you want to put it in your notes, maybe you don't. I'm going to put in a little extra notation of what I actually did below, because technically this is the fundamental theorem of calculus. It's good the way it is. But how I actually solve it is I find the antiderivative. And I find it with, what do I want? I want a bracket with a top and bottom. I can do this, I think. No, what just happened? That's okay, I'll do it again.
I have them on.
Wait, what?
I have Invisalign.
Why are you okay? What?
I've had Invisalign for 2 years.
He's really never. He's never had braces. Wait. I'm confused.
Why isn't it working?
No, because I've had Invisalign. I guarantee you never want to have braces, but they act like braces.
Sorry guys, this is being really annoying and weird. I don't know why.
You know, this smells like.
Oh, goodness gracious. So I just deleted my page without asking.
It's it.
Try to dance back.
It's it. I don't want to do this anymore.
You're like. Okay, man.
Just
know it works. Just know it works.
Alright guys, well my smart is just really mad at me I guess because it's not doing anything I wanted it to. Here's what I meant to write even though the entire page of notes just disappeared because that's cool. The forever card is just going to
You're so right.
What? To be honest, guys, it's going to be too much for you to try to do it all at once. So my advice is to go ahead and find the antiderivative. Then you go ahead and just remind yourself of your bounds from A to B, and then you plug in. Now be careful. The AP, guys, if you show a lapse in logic or you show a gap in understanding as far as your work, meaning if you were to say that a definite integral equaled the antiderivative, you would be wrong and they would take off points, even if you later on plugged in B and plugged in A appropriately and then solved and got it right. So if you're going to show the antiderivative, which I hope you do, and it's going to take time, it's going to take work, we have a whole homework on it, right? You're going to need to write the antiderivative, but you need to write your bounds at the end of it. And usually the antiderivative is messy and long. You can close it in brackets. You can close it in parentheses. I usually do parentheses because I'm using the brackets for the bounds. But either way, you can use brackets, you can use parentheses. For your antiderivative, you're going to have to, if you're saying it equals, you have to put your bounds on the end and then go ahead and plug in. Remember, antiderivative at the top minus antiderivative at the bottom. So that's probably the best notation to put into your fundamental theorem of calculus card. Some people call this part 1, some people call this part 2. There's like a whole debate. There was a college professor in Berkeley that got all mad about some of the textbooks. The nice thing is she agreed with our AB textbook being right, and she disagreed with the BC textbook because CalcAB switches the parts. And she says that that's wrong. But I don't know. Either way, it's the fundamental theorem of calculus leaves part. So if I was to give you this and say solve, rectangles? No. Trapezoids? No. Antiderivative? Rectangles? No. Trapezoids? No. Antiderivatives?
Yeah.
Yes. Okay. Just making sure you're okay.
No.
It's okay, I was like trying to figure out what makes sense.
No.
Okay, so this is an easy one as long as you know your rule. Negative sign.
There we go.
Was I writing?
Right.
You guys agree?
Yes.
Wait.
Are we done?
No.
Wait.
Where's the plus C? It's a definite interval, not an indefinite. We're not writing a function. We're just trying to figure out the change. The change in the original. The change in the amount given the rate. So then,
You find the interval.
Good job, Mariah.
You find the interval.
Is that wrong?
why is she wrong? Adam, say it loud.
Because when they direct sign, it's so close.
And yet,
So close.
So
We
far.
would have gone without
because the multiple choice would have been.
Fine.
But,
Fine.
one more time. Adam,
80%.
why were you taking the derivative of sine?
To check.
To check, because you can always check any antiderivative by deriving. What's the derivative of sine? Positive cosine. So what's the antiderivative of cosine? Positive. Now, if this is a long answer, technically you could go ahead and box it and be done. That's what I learned. You don't have to go to the unit circle, but for multiple choice, you would have to keep going. So, what is sum of pi? What is sine of 0? 0.
So if you could say.
Yeah, it's
Wait, how does this make sense? Well, hold on. Shouldn't we actually, don't worry, this is what you have to do every time. But don't we actually know what cosine looks like? Whoa, why is he so high? Why is he so low? Because he's been stretched. He goes down -2 and up 2. Adam, here's what I was saying about the whole above and below thing. From 0 to pi over 2, there's a positive displacement. But all my trig curves are symmetric. So when I go from pi over 2 to pi, I have the exact same area but negative. So it moved right because of that positive displacement with a positive velocity. It moved right this area, and then it moved left that area, and guess what happens?
So like a changing contrast dimension. But symmetrical things.
Symmetric is key. If it wasn't symmetric, it would be strong.
Wow.
Ready, set, go. You guys can work in your groups, talk it out. I'm not gonna explain it because my voice is dying anyway. I'm gonna solve it.
I didn't get the understanding of it, but I understood math.
He works hard.
Basically, MBT guarantees there's a perfect rectangle that equals the subtraction of antiderivatives. If we add them all up, we get one big old subtraction.
No movement process.
Yeah.
Oh, I mean, and then you split up.
You guys hearing that you have to distribute or else you're not going to be able to solve it?
The power of
Go back and find it. When you multiply, it's the same. But because that is. Sorry. What's our next project, Chris? Nice.
Technically, section 4.4 is the end of before our next test.
Oh boy.
Can we box this one?
The forever quiz is on Monday.
Oh, so
Our test is on Tuesday. But I have split up the test into 2 parts. The test review is due Monday. That'll be coming up on Google Classroom probably tomorrow. Friday, we're going to have the first part of the test, which sounds weird, but the first part of the test has very little to do with fundamental theorem of calculus and antiderivatives and areas and Riemann sums. The very first part of the test is there is a motion word problem or 2. And so I'm letting you totally split up your studying so that we can do like a motion word problem, which has a good number of points. And you can study the 4.1b for that part of the test. And then next week will be the rest of the test. If you heard any of that. All right. Your antiderivative, you should have rewritten first before even trying.
This is not important. No. I knew it. Can you box this one though?
Do you guys put your anti-derivatives in parentheses?
Can you split the integral, right, or you did this integral of both, and then you did a definite integral for like both things? Will that give you the same answer?
Yes.
Okay.
You can make it a bracket or you can make it a line. Because the addition, I need it to be grouped.
Is it like a limit where you can't get rid of it until you plug it in?
Yeah.
Oh, but you put a bracket on both.
I bet that can simplify down. Oh, bummer. Chop this guy.
Chappelle.
That's okay. That's another reason why I think most of our tests is next week. Guys, you heard the forever quiz is coming Monday, so get those cards. You heard that motion, 4.1B, that part of the test is on Friday. Everything else is pushed to next week, including the review we'll do on Monday. So practice test is coming, test review is coming. Yeah.
To do this, right?